Okay, so welcome to the next unit in the electromagnetism topic. Okay, is actually the big one, electromagnetism. Okay, so I've moved on from magnets and I'm going to now introduce electricity to the equation. So the learning objectives, by the end of this shorter unit, you'll understand that electrical current in a conductor produces a magnetic field, and you'll be able to describe the construction of electromagnets and sketch and recognize magnetic field patterns for a straight wire, a flat circular coil, and a solenoid when each is carrying a current. So what is electromagnetism? Well, in 1820, Danish scientist Hans Ørsted noticed that his wire, which had electricity passing through it, caused his needle to deflect. So without any electricity passing through it, you can see that there's no current. The current compass is just pointing north as normal. But then when he put electricity through the wire, the compass deflected, suggesting something was happening. Okay, so then along came a Scottish physicist named James Clerk Maxwell, and he showed there was actually a relationship between electricity and magnetism. In fact, they're pretty much different sides of the same coin. They have a certain symmetrical relationship with each other. So he said, well, if you change electric field, you should be able to produce a magnetic field and vice versa. So that's what actually was happening in Ørsted's work. The electrical current was actually producing a magnetic field around the wire. And you can see this example here by this animation here. You can see that as soon as electrical current is passed through this loop of wire, it's beginning to align those iron filings and form a magnetic field. And when you turn it off, the magnetic field disappears. So what we're going to do now is look at the different magnetic field patterns that you see around wires. And the first example we're going to look at is the simple straight wire, very similar to the one that Ørsted worked with. Okay, so you can see from the diagram that the blue line is the wire, and current's being passed through the wire, and a magnetic field forms around the wire, which is illustrated by those concentric circles of green around the wire. And the field consists of these concentric circles, and the magnetic field is strongest near the wire. And you can see this because the distances between the magnetic field lines are closer to the wire and further apart as you go further away from the wire, which you can see there. And the strength of the field increases if you increase the electrical current. Okay, so those concentric circle, the distance between the concentric circles is going to decrease if you increase the current going through that circuit. So in terms of what the direction will be for this magnetic field, we use something called the right-hand grip rule. Okay, so here is my trusty wire right here, and we're now going to use the right-hand grip rule to work out the direction of the magnetic field, which way it goes around the wire. Okay, so if we have a wire here and the current is going up, okay, then we get our right hand and then we grip around the wire. The thumb is going to be placed in the direction of the electrical current. Okay, the thumb, and what's going to happen is that the fingers show the direction of the magnetic field. Okay, so they're going to be going around in this direction. Okay, I guess anti-clockwise in this particular case. Okay, so that's how we use the right-hand grip rule for fields. Okay, so here are 4 examples. So you need to complete the diagrams below to include the direction of either the field or showing the direction of the electrical current. The important point to note is this one here, which you may not be familiar with. Okay, so a dot on the wire means that electrical current is going out of the page towards you, and electrical current going into the page is shown as a cross. Okay, so and the way I remember this is thinking of it like an arrow coming towards you. So if the arrow is coming towards you, the arrow head is going to be seen first, and it's going away. The arrow crosshairs of the feathers are going to be seen as it going away from you. Okay, so let's do these 4 examples now. Okay, so the first one, we've got to add the field arrows. Okay, so here is our trusty wire example here. So we're told that the electrical current is going away from us. Okay, so we're going to get our right hand, and we're going to basically move the thumb so it is now moving into the page, and you'll notice that the current is therefore going clockwise. Okay, so we should be able to draw the arrows in, okay, going, whoops, not quite right, that's anti-clockwise, going clockwise. Okay, and then for the second one, we said to add the current direction. Okay, so we are basically putting our hands around so the current is going this time anti-clockwise, so it means it must be coming towards us, I hope. We're going to check, of course, if we're right very soon. So it's going to put a little dot in the middle. Okay, and then we're going to add the current direction for this one, so it's going, again, the right hand rule, it's now going a bit of jiggery-pokery. It's going, okay, again, it's going into the page this time because the electromagnetic field is going clockwise, so that should be into the field. So it's going to be a cross. And using our logic from the first example that we've did, well, if it's going into the page, it's going clockwise, so that means if it's going out of the page, it must be going, let's do a bit of job at that arrow, it must be going anti-clockwise. Okay, so let's just test if we've got those 4 correct using our right hand grip rule. And indeed we are correct for that one. It's a dot, good, and it's a cross, and it's going anti-clockwise. So we got it correct. Excellent. Okay, so this is the second example we need to know. It's the flat circular coil. So that's it in 3 dimensions. So basically you've got a loop with a current going through it, and you can see from above that there is a uniform field going right down the middle of the flat circular coil, and they kind of look like eyes, really, little cat's eyes. But you can see there is the 2 different parts of or different halves of the coil produce their own magnetic field, and that's what it actually looks like. So you have to be able to sketch that. And the final example is a solenoid. Okay, so that's where the wires are looped around like into a cylinder. Okay, so the cylinder is actually made of the wire, or a coil of wire carrying electrical current. That's the example there. That's what it looks like. Okay, and the magnetic field is similar in shape to that around a bar magnet. Okay, so just think of it as basically a glorified bar magnet. Okay, with the southern pole and the north pole. And the strength of the wire again will of course increase in 2 ways: by increasing the current, of course, which is the same with the loop and the circular wire, but also by increasing the number of turns in the coil. And there we go. So the right hand grip rule for poles is the following. So this is for solenoids. So if you grip the coil with the right hand, okay, just like that, more kind of a duck's hand, but still, that's an animation, so that's a hand. The fingers are placed in the direction of the current flowing around the coil, okay, and the thumb therefore points towards the north pole of the end of the coil, okay, fielding north. So that's the right hand grip for pole. Okay, so welcome back, and now let's try and complete the diagrams below. using the right-hand grip rule this time for solenoids. Okay, so I'm going to use my trusty solenoid model. Okay, so just imagine this is now a coil of wire. So let's try and locate the north in the first example. Okay, so right hand, solenoid in hand, the wire is, the current's going around that way in the wire. The direction, therefore, is going to be going this way. So it should be, that should be north and that should be south. Okay. Second example, locate the south. So here we go. The current's going that way. That means that the magnetic field must be going down. So it must mean that that must be north and that must be south. So that's the south there. Add a direction current. So again, the wire here, direction of the magnetic field is going down to the north. Okay, so that means that must be the south. And it means that the current is going up the wire, as it were. Okay, and the final one, and I'm no artist, is add the coils. So it's going to be going there we go with my great artistic work. So let's see if we got that correct. Okay, there we go. So the first example is correct. That is indeed North Pole. That is indeed the South Pole for the second example. That is the correct direction of the current in the third example. And my great artistic impression, adding the wires to the coil, that is how we do it. Okay, so that's pretty much how you use the right-hand grip rule for both solenoids and for simple wires. And next lesson we're going to look at ways in which we can create or induce electromagnetism in wires.